Hello, how's it going? I know it's been a while since I did any math videos, but I really like math, and today I want to talk about one of, hands down, the most important operations, algorithms, whatever you want to call it. It's the dot product. If you're doing game development and you don't know what the dot product is, first of all, good luck. But secondly, you may find that as you go along and do geometric tests and everything, that there's a bunch of weird formulas that you've used, and then later on it turns out that actually they were the dot product. They just weren't being called the dot product at the time. Anyway, so let's say we have a vector. Here we are. I'll do a three-dimensional vector, but this dot product generalizes to an arbitrary number of dimensions. Mathematically, there's a definition for the dot product, which is like, how do we compute it numerically, right? And it's just taking the element-wise, what am I doing? Taking the element-wise product of the components in each of the dimensions and then summing those together, just like that. And if that was all we could do with the dot product, it wouldn't be very interesting. But thankfully, it has a geometric interpretation. Let's say that we've got the origin there, and these vectors, well, they're three-dimensional. So there we are. I'll put one of them here, one of them here. Doesn't really matter what they look like. Let me just sort of sketch that. Just for context. We can interpret these vectors as directions from the origin. And because both directions are coming from the origin, they have an intersection point. And because they have an intersection point, even though they are three-dimensional, they do have an angle between them. And furthermore, each of them has a length or a magnitude. So that's the length of the vector A. And down here, this length is the length of the vector B. Cool. So the geometric interpretation of the dot product of two vectors is it's equal to the magnitude of the vector A times the magnitude of the vector B times cosine of the angle between them. Now this is super, super cool. This shows up in so many things. For one thing, we don't even have the angle, right? We don't even have the angle. We have the cosine of the angle, and that's even better. And the cool thing about having the cosine of the angle is the cosine of the angle is a function which is maximized when the angle is 0. So it's maximized when two vectors are completely parallel. There are many consequences to this. One consequence to this is that if I take the dot product of a vector with itself, I was going to write b there, but anyway, that will be the magnitude of that vector times itself, so that number squared, times cosine of the angle. But any vector is completely parallel with itself, so it has an angle of 0, and cosine of 0 is 1. So in other words, if I take the dot product of a vector with itself, that gives me the square of that vector's magnitude. And then, this is a really cool part, I can then say, all right, if I want to get the magnitude of a vector, the length of a vector, all I need to do is take the dot product with itself, which as you can see above is a well-defined operation, and then take the square root of that number. How cool is that? Many other applications. Let's say we have a surface. I'm viewing it from top down, a plane or something, a triangle, whatever you want. And that surface has a normal vector. That's a direction vector with a length of 1, which is oriented such that it's 90 degrees to the surface, to the triangle, however you want to imagine it. And let's say that I have a light source, and I want to apply lighting to this surface. The amount of light on this surface will be maximized when the light source is shining directly onto the normal vector, like that. And then when we go a little bit off, it's still pretty bright, but it's reduced. And then it sort of keeps reducing, just like that. But wait a second. We have a way to calculate how parallel these vectors are. Let's say that I take the direction vector from the point to the light source. I'll call that vector PL. And then I normalize that. So I shrink it down such that it has a length of 1. I'll call it PL normalized, something like that. And this is my normal vector here. So what we've got is if I take the dot product of the normal vector and the normalized direction vector to the light, well, this will indicate how much lighting to apply to that surface. By the way, it could also be negative. So if I have a light source back here on the back side, then the angle there will be obtuse. That will be a negative value. So you sort of cap it at 0. So we say, take that dot product and 0, whichever is larger, and that's your lighting coefficient. That's one example. Here's another example. Let's say I am a player like that, and some sort of bang has occurred. Bang, it's emanating outwards, sound waves. And I want to work out the panning for that sound effect. So let's say I have my forwards vector here, I have my right vector, and I want to work out, should this sound effect be played on my left side or my right side? Well, what I can do is I can take a direction vector from my position out to the sound source. We'll call that vector A. Then we normalize that, so we shrink it down to have a length of 1, just to make the math nice. That's normalized A. And then I take the dot product. Whoops, there we are. The dot product of that vector with my right vector. And that will indicate the panning amount. If it's a positive number, then it's an acute angle and it's here on my right side. If it's a negative number, then it's an obtuse angle and it's here on my left side. I mean, there are many, many examples. One more example. Let's say that we have an irregular, convex shape like this, convex polygon. And each of these polygons has some sort of normal vector, sort of indicating the outwards direction. Let's say we have a point. Oh yeah, in addition to that, every polygon has like an end point. Okay, now I'm going to do a test to indicate whether a point is inside this polygon. Let's say I've got point A, B, and C, for instance. Now what I can do is for each boundary line, I can take something like that, some displacement vector from the start point of the line out to the point. Okay, so we can use the dot product to measure whether a point is sort of outside or inside, on the outside or inside region partitioned by a line. And the space inside this polygon is the intersection of the inner regions of all of these partitioning lines. And so we have a quick test. This point needs to be inside all of these lines. The moment we see a line, we test it, and it says, oh, this is on the outside region, or however you want to measure it. Then we can discard that straight away, early exit, and say, what? We're not inside that polygon, which gives us a quick way to do collision detection or region detection, check if we're inside a region. Those are some mathematical properties and examples of the dot product. Now for something a little more concrete, and that is calculation. So, want to first up find the regular straight dot product. Then we want to find the magnitude of these vectors individually, and then find the angle between them. So, let's go first up. The dot product of u with v is 2 times 1 plus -1 times 1 plus 1 times 2. This is a lot of fun. And this comes out to 2 minus 1 plus 2, which is 3. Okay, very cool. 3. Now, let's find the magnitude of u. So the magnitude of u will be the square root of the dot product of u with itself. So we have 2 times 2 plus negative 1 times negative 1 plus 1 times 1. Why did that take me so long? And this is 4 plus 1 plus 1, which is root 6. And then we'll go ahead and we'll find the magnitude of v, the norm of v, and that's just the same as before. So we have 1 squared is 1, 1 squared is 1, 2 squared is 4. So these vectors actually have the same length. Okay. Now, we need to find the angle between them. This is a little more complicated. Well, let's start with the facts. We know that u dot v is equal to the magnitude of u times the magnitude of v times the cosine of the angle between them. Okay, now we know some of these numbers. We know that u dot v is 3. We know that each of these is root 6. So then root 6 times root 6 is 6. Divide both sides by 6. We have 3 over 6, which is 1/2. And then we're saying, okay, what's an angle that when we take the cosine of it, it's 1/2? And that is 60 degrees. Or if you like radians, it's pi on 3. Cool. Okay, so that's been an on-paper example. Let's have a look at implementing that in code. Okay, so here we are in our code, and like I said, it has been a long time. It's been a hot minute since I last looked at this, but I'm going to put in a few functions. Like I said, all of these concepts generalize across dimensions, so I'm going to be copying these over, whether they are vec2, vec3, or vec4. To start with, we'll have the dot product. So to take the dot product, this function will return a float, and it will take in a reference, read-only reference to a vec2 and another one. Okay, so what we'll do is we'll return a sum, and if we look up here, we see that we have the chunk of SIMD memory, but we also have a view into that SIMD memory with the elements method, or the elements data field. So I'm going to access the elements. So I'll say we'll go u element 0 times v element 0, not 1. And then we'll do the same thing. Now I did try looking into more SIMD style operations on this, and I found that ultimately just doing this was faster. Because we got a whole bunch of numbers, we got a whole chunk of memory, but there is some overhead in swizzling that memory down into a single number. And so in this case, it just so turns out that doing it element-wise is the way to do it. So what I'll do is I will also bring this down. I'll do the same thing for vec3. And this will be very similar. We'll just add in that extra Z component. Okay, there we have it. And we can do the same thing for vec4. I don't know why you'd want to take a dot product with vec4, but mathematically you can, so let's do it. Okay, cool. So that's all well and good. Now let's go back to our main function and we'll implement this. So I'll go over to my source, and I'm going to modify this quite a bit. I'm going to pare it down a lot. Just going to get rid of this vec2 stuff. And yeah, and the vec3 stuff, which is actually vec4. Okay, so I'm just going to do the example that I had before. So I have the vectors u and v. I said v. And these will be, what is it? 2, -1, and 1. And then for v, v will be 1, 1, and 2. Okay, cool. So now I'll print this out. I'll say, alrighty, the dot product of u and v just like that. Cool. Let's now take a look at that. Yep, awesome. Yeah, so the dot product of those two vectors is 3. Very cool. Now, let's take this a little further, and let's get the magnitude. Or, as it's sometimes called in math, the norm. So, just go back up to my vec2, and I'll make a function. This function is going to return a float. It'll be the norm, and we want to get the norm of a vector. Guess it doesn't really matter whether we call this u or v. So what I'm going to do is I'm going to need to take the square root. So in order to do that, I'll include the math library. So I'll just include math. There we go. And we're just going to return the square root of the square of the magnitude, which we know is the dot product of the vector with itself. Okay, cool. And then again, I'll just generalize this down below. There we go. Excellent. A lot of fun. And let's have a look at that. So let's get the norm of all these functions. So we'll go norm of u just like that. And then the norm of v. Cool. Okay, let's test it. So remember, both of these were the square root of 6. Let's find out. Okay, that looks like the square root of 6 to me. 2 squared is 4, so happy with that. Okay, excellent. So now let's make another function which will take in a vector and normalize it. To normalize a vector, we need to get it to have a length of 1. We can do this by dividing each of the components by the vector, the norm of the whole vector. So let's go ahead, and this will be super, super quick. I want to produce a new vector. The function will be called normalize, and I'll take a vec as my input. So what I'll do is I will take 1, over the norm of the vector, multiply that by, use that as a scaling factor, get a copy of v which has been scaled by that amount, and that's my normalized vector. I'll do the same thing for all the other vector types. There we have it. Oh, whoops. Oh my goodness. I need more coffee or something. Okay, cool. So let's super quickly go through it. I'll go normalize that vector. Just like that. Awesome. Okay. So as we can see, these vectors have been shrunken down. They have the same fundamental direction, the same fundamental proportions. They just have a length of 1 now. Cool. So we've sort of covered a lot of ground today. We've had a look at the dot product. We've had a look at its geometric interpretations, as well as some examples of applications, and we've gone ahead and implemented it in our own math library. I hope you enjoyed this, and I will see you again soon. All right, have a good one. Bye.